This video introduces standard position. An angle is in standard position if its vertex is at the origin and its initial side is on the positive x-axis. This diagram gives us an angle in standard position. We're going to do this a lot in trigonometry. So our initial side coincides with the positive x-axis, and then our terminal side is just somewhere else. An angle in standard position is said to lie in the quadrant in which its terminal side lies. So this would be a quadrant 2 angle because its terminal side is in quadrant 2. Angles in standard position having their terminal side along either the x or the y axis are called quadrantal angles. And we've got 4 of them. Right, so if our angle is 0 degrees, here our terminal side is just right on top of our initial side on our positive x-axis. We have a quadrantal angle at 90 with our terminal side ending on our positive y-axis. Another one when we're at 180 degrees, terminal side on that negative x-axis. And then lastly at 270 degrees with our terminal side on the negative y-axis. We've mentioned before that a complete rotation of a ray results in an angle measuring 360 degrees. But by continuing the rotation, angles of measure larger than 360 degrees can be produced. It's kind of like being on a racetrack and just going around over and over and over again. The distance that you've gone continues to increase even though you're just going on the same track. Well, that's the same kind of thing that's happening here. By continuing the rotation, we get these larger angles. 2 angles that have the same initial side and the same terminal side but different amounts of rotation are called coterminal angles. And coterminal angles always differ by a measure . Two angles that have the same initial side and the same terminal side but different amounts of rotation are called coterminal angles. Their measures differ by a multiple of 360 degrees. Again, using that racetrack analogy, it's like if here's the starting line and you're going around, here you're right back to the start, but when you do a second loop, you get right back to the start. So you started at the same spot, you're ending at the same spot, but you've gone more trips around the track. Now, that's what's happening here as well. And coterminal angles are always differing by multiples of 360 degrees because 360 degrees is one trip all the way around the track. So let's find the angle of smallest positive measure that's coterminal with each of these angles. Well, our answer should be something between 0 and 360 degrees. You'll notice that our first angle, 419 degrees, is more than 360, which is our max amount in one rotation. So we are going to subtract 360 degrees. We end up with 59 degrees. This falls in between 0 and 360. So this is the smallest positive measure that's coterminal with 419. Our next example, you'll notice, is a negative number, negative 98. And we need our answer to be something between 0 and 360. So this time we are going to add 360 to our negative 98 degrees, and that'll give us a coterminal angle between 0 and 360. We end up with 262 degrees. Our last example is a large positive number. We're going to start it the same way we did the first example in this grouping. I'm going to start by subtracting 360 degrees. When we do that, we get 1,294. That number is still larger than 360. So we're going to subtract 360 another time. That gives us 934. Still too big. I'm going to subtract 360 again. And in reality, I'd just be doing this on my calculator. 574, still too big. Gonna subtract 360 again. 214. Finally, a number between 0 and 360. This is our smallest positive angle that is coterminal with 1,654 degrees. So to find a coterminal angle, you're just adding or subtracting 360 repeatedly until you get a number that falls between 0 and 360. In these next examples, we want to give an expression that generates all angles coterminal with each angle. And we're going to see directions like this, all angles coterminal with each angle, at the very end of the course, well, towards the end of the course, as we are solving trigonometric equations. We do the same thing every single time we want to represent all angles coterminal with an angle. We know that coterminal angles measures vary by a multiple of 360. So we're just going to take our angle, whatever it is, and tell it that we want to add or subtract multiples of 360 degrees. And the way that we do that is by saying plus 360 times n, where n is an integer. Remember that integers are positive and negative counting numbers. Now there is some shorthand notation that we can use for saying n is an integer. The shorthand notation I would use is n, and then this weird looking e means is an element of, and then a bold-faced Z is the abbreviation for integer. We've seen the bold-faced R before to represent all real numbers. Well, the bold-faced Z represents all integers. So every single time, you're just going to take the angle plus 360n, where n is an integer. So the expression that generates all angles coterminal to negative 188 degrees is going to be negative 188 degrees plus 360n, where n is an integer. And then one more example, same thing. 210 degrees plus 360n, where n is an integer. And the fact that n is an integer takes care of the adding and subtracting, because integers are the set of all positive and negative counting numbers. Our last example in this video says that a windmill makes 90 revolutions per minute. We want to figure out how many revolutions does it make per second. So this is more of a dimensional analysis, a changing of units more than anything else. So we have 90 revolutions per minute. So I'm going to write that in a fraction form. 90 revolutions per 1 minute. And now we want to rewrite this as revolutions per second. So all we need to do is change the time unit. And we can do that by multiplying by a unit fraction that relates minutes and seconds. We know that 1 minute is equal to 60 seconds. I knew that minutes had to be the numerator of the fraction because I need minutes to cancel with the minutes in the previous fraction. And now we can go straight across. In our science courses, when we typically see this, rather than seeing the unit fraction, remember a unit fraction is just a fraction that has a value of 1, rather than seeing the unit fraction written like this, a lot of times in science when we're doing it, and they call it dimensional analysis, you'll see it written like a table like this. So it's the same thing. I'll use them pretty interchangeable. Maybe I use the table a little bit more. Now that we have eliminated our unit of minutes, we can multiply straight across. We get 90 revolutions per 60 seconds, and then we want to simplify. We're going to do 90 divided by 60, which will give us 1.5, and then our unit is revolutions per second, which is what we're looking for.